In the last lectures, we discussed sequence of events, that is infinite sequence of events and limits of these events, lim sup we define, lim sup, and lim, suppose sequence is n, this event we defined. Similarly, lim inf as n tends to infinity, this type of limits we defined, and then how to find out the probability for these limiting events. We discussed different theorems and particularly Borel-Cantor dilemmas, how to find out this probability of lim sup n under two different conditions. Now, this application of convergence of infinite sequence of events is the convergence of sequence of random variables. Now, we will be discussing the convergence concepts for random variables, and these concepts are useful in many practical applications, just like it is the basis of stochastic calculus. Also, we will be discussing very important applications like central limit theorem and with laws of large numbers. First of all, let us see what is convergence of a sequence of real numbers. Consider a sequence of real numbers xn and going from 1 to infinity. This sequence converges to a limit x. If corresponding every epsilon greater than 0, we can find a positive integer n such that x mod of x minus xn can be made smaller than epsilon for all n greater than n. So, what does it say? That this difference between the limit and the sequence can be made as small as possible, where alpha, epsilon is an arbitrarily small number, positive number, for sufficiently large n. Then we say that xn converges to x. So, for example, if I consider this sequence, suppose xn is equal to 1 by n, simple example. Now, we know that limit of 1 by n as n tends to infinity is 0. Now, how it conforms to this definition? Suppose for any epsilon greater than 0, we can choose a positive integer n greater than 1 by epsilon. So, that in that case 0 minus xn mod of that will be 1 by, that is equal to 1 by n, and this will be less than epsilon. So, because we are considering n is greater than 1 by epsilon, therefore, for any n greater than capital N, this will be valid. So, that way this 0 will be limit of this sequence. Now, we have to extend this definition of convergence or limit to sequence of random variables. Consider a sequence of random variable xn and going from 1 to infinity defined on SFP. We are defining, suppose, a sequence of random variable. Now, what does it mean? That means if we have a sample space, suppose S, this is the sample space, and now corresponding to suppose any element S1 here. So, that will map to, suppose this is my time axis, n is equal to 1 here. So, n is equal to 1, it will be 1 point. Similarly, n is equal to 2, it may be another point. Like that, this S1 will be mapped to different points at different instant of time. So, that way I may get a sequence, maybe if I join, this may be something like this. So, that means corresponding to every sample point, I will get a sample functions like this. So, that means for each S belonging to sample space x1s, x2s up to xns, represent a discrete time sample function particular for each s. So, that will be we will have a sample function like this. Therefore, since the sample space will contain other sample points, therefore, corresponding to each sample point we will get a sample function like this. So, unlike sequence of real numbers, xn sequence of random variables represents a family of sequences. So, each sample function is a sequence, therefore, it is a family of sequences. And here lies the problem in defining the convergence for the sequence of a real numbers. So, convergence of a random sequence is to be defined using different criteria, because it is, since it is not a single sequence, we have to use different criteria to define the convergence of a sequence of random variables. Therefore, there are different modes of convergence of a sequence of random variables. The most elementary convergence concept is convergence everywhere or pointwise convergence. It is also called pointwise convergence. A sequence of random variables xn is said to converge everywhere to x if limit of xn s equal to x of s for all s belonging to s. So, suppose corresponding to each sample point we will find a limit. So, in that case this is the pointwise convergence or convergence everywhere. We can consider one simple example. Suppose define a sequence of random variables. Suppose x only sample space comprises of two sample points s1 and s2. Now, suppose xn s1 is equal to 1 plus 1 by n and xn s2 is equal to minus 1 plus 1 by n. We observe that as n tends to infinity, this point will become 1 and this point will become minus 1. So, that way we can now define the limit a random variable x such that suppose x of x1 is equal to 1 and x of s2 is equal to minus 1. So, obviously limit of xn s1 will be 1 and limit of xn of s2 will be minus 1. Therefore, in this case this sequence xn, this xn sequence converges pointwise or converges everywhere to random variable x. So, that way convergence everywhere is just an extension of convergence of a sequence of real numbers. So, here we are not considering the property of the random variable, we are simply considering this as a sequence of function. Next, we will consider one concept which is known as convergence almost sure or convergence with probability 1. This is also known as a strong mode of convergence. This is strong convergence. Let us consider an event, that is, it is comprising of points s such that limit of xn s is equal to xs. So, we are considering all those sample points for which limit of xn s is equal to xs. There may be some sample points where this limit is not equal to xs. Okay, but we are considering only those sample points for which this limit is equal to xs. Since this is an event defined on SFP, we can find out the probability of this event. This sequence now xn is said to converge to x almost sure or with probability 1 if probability of this event, that is probability of the event s such that limit of xn s equal to xs is equal to 1. So, probability of this event is equal to 1. So, that is the definition of almost sure convergence. That means, wherever there is a convergence, so those sample points if we consider, then the corresponding event should have probability 1. Equivalently, for every epsilon greater than 0, there exists n such that a probability of this event is less than epsilon for all n greater than n. This is the event we are considering, that is S such that xn S minus xs mod of that is less than epsilon for all n greater than certain n. Suppose epsilon corresponding to each epsilon, we will get a big n number, and suppose where this convergence takes place for all n greater than equal to n, that probability is equal to 1. We write xn converges to x almost sure. This is the symbol we use. As I have told, this is a mode of strong convergence. Let us consider one example. Suppose sample space is S1, S2, S3. It comprises of 3 elements, and xn be a sequence of random variables with xn of S1 is equal to 1, xn of S2 is equal to minus 1, and suppose this is a diverging sequence, xn of S3 is equal to n. And now we will define another random variable on the same sample space. xs1 is equal to 1, xs2 is equal to minus 1, and x of s3 is equal to 1. So here it is diverging, here it is 1. And therefore, if I consider the event for which this convergence is taking place, we see that xn s1 is 1, and here also 1, xn s2 is minus 1, here also minus 1, but xn s3 is n, here it is 1. Therefore, it is not converging for s3. So that way, this event now where that convergence is taking place, that is that comprises of s1 and s2. Therefore, probability of this limiting event now is equal to probability of s1 s2. So when xn will converge to x almost sure if probability of this event is equal to 1. So that way the basic concepts of almost sure convergence is introduced. Now how to test almost sure convergence? Xn converges almost sure to x if probability of this event s such that limit of xn s equal to xs, the probability of this event is equal to 1, or equivalently if this limit is not equal to xs, if we consider that event, that probability should be equal to 0. Now let us define a set of divergence where xn s is not equal to s. So that event is, we are calling this event as D. Now that event is equal to the set S such that mod of xn minus s, mod of xn s minus xs is greater than equal to epsilon. Now infinitely often for all arbitrarily small epsilon greater than 0. So what we are defining, that the set of divergence is this set comprising of element such that mod of xn s minus xs is greater than epsilon infinitely often for all arbitrarily small epsilon greater than 0. So if suppose there is only divergence in the case of finite number of n, then we can always consider the sequence starting with that number where it is diverging. Suppose after that the sequence we can consider. So that way this is important that we define the event s such that mod of xn s minus xs is greater than equal to epsilon for infinitely many n, because if it is finitely many n, then we can always go beyond those numbers to find out the convergence sequence. Now for each arbitrarily small epsilon, we can find a positive integer m belonging to set of natural number. This is the set of natural number such that 1 by m is less than equal to epsilon. So any epsilon you consider, we can get a positive integer like this such that 1 by m is less than equal to epsilon. So that we can replace epsilon by 1 by m. What is the idea? Because if it is in terms of m, we can enumerate. So this set of divergence now we can define as D is equal to the set comprising of element S such that mod of xns minus xs is greater than equal to 1 by m. Instead of epsilon, we are writing greater than equal to 1 by m infinitely upon for all m belonging to n. That is equal to, suppose now m is, we can count m, therefore we can write in terms of suppose union of dm, m going from 1 to infinity, because all m we have to consider. So that way we have defined a set of divergence where the random sequence diverges from xs. So that we are considering, and that is a union dm, because for each m we have to define that divergence set. So union dm, m going from 1 to infinity. Now we will get a condition for as convergence in terms of d. Suppose this set of divergence can be rewritten as we have already done, that it is a union of dm, m going from 1 to infinity. Now this infinitely upon, that is the limb soup of S such that mod of xns minus xs is greater than equal to 1 by m as n tends to infinity. That is the event of this that xns minus xs, absolute value of that is greater than 1 by m infinitely upon, that we are writing in terms of limb soup. Therefore now this is equal to, as from the definition of limb soup, intersection n going from 1 to infinity of union j going from n to infinity of the event s such that mod of xjs minus xs is greater than equal to 1 by m. So this is the basic event where it is greater, this deviation is greater than 1 by m. Then we are considering the limb soup of that event sequence. Obviously now xn will converge to x almost sure if and only if probability of union of dm is equal to 0. So we have the condition now, if and only if condition, that xn will converge to x almost sure if and only if probability of union of dm, m going from 1 to infinity is equal to 0. This is a very strong condition. Now we will, because here we have the union of dm, m going from 1 to infinity, this condition we want to simplify. We will state a theorem. The sequence xn converges almost sure to x if and only if probability of dm is equal to 0 for each positive integer m. So this is a simpler condition, because we have to consider p of dm instead of the probability of union dm. Now as a proof, suppose xn converges to x almost sure, then probability of union of dm, m going from 1 to infinity must be equal to 0. But we also know that this dm, any member is a subset of the union di, I going from 1 to infinity. Therefore we can write that probability of dm, because it is a subset, it is a less than equal to probability of this union. But we know that probability of this union is equal to 0, therefore probability of dm must be equal to 0. So that way, if xn converges almost sure to x, then probability of dm must be equal to 0. Now next, if probability of dm is equal to 0 for all m greater than equal to 1, then probability of union of dm, I know that is less than equal to sum of the corresponding probability. This inequality we proved earlier. Therefore, and I know that each of this probability is equal to 0, therefore probability of this union will be equal to 0. So that way we have proved that xn converges to x if and only if probability of dm is equal to 0 for each positive integer m. So this is a condition, that is if and only if condition. Probability of dm is equal to 0 gives a necessary and sufficient condition for almost sure convergence. So we can find out this probability to prove almost sure convergence. But this is still a difficult task, because we have to consider dm, then dm is dm for each m, and we know that dm is defined through that limb soup operation. Now we will state a theorem that is which is a consequence of first Borel-Cantelli lemma that gives a sufficient test for almost sure convergence, that we will discuss now. Theorem: if for each m greater than equal to 1, now we are considering this sum, probability of mod of xn minus x greater than equal to m. So this is for each n we will consider and then sum up. So therefore infinite sum of probability of mod of xn greater than equal to 1 by m. So if this infinite sum of the infinite series is less than infinity, then xn converges almost sure to x. So we have to consider the probability of deviation for each m and then sum up. If this sum is less than infinity, then xn converges almost sure to x. Suppose for each m greater than equal to 1, this sum is convergent. So what does it mean? Now we can apply the Borel-Cantelli lemma if this sequence of event, suppose I can consider this as a sequence of event. If the probability of this sequence, if the sum of the probability of this sequence is less than infinity, then probability of limb soup of that event sequence is equal to 0. That is the Borel-Cantelli lemma 1. So what we will get here? This implies that probability that limb soup of the event as such that mod of xn s minus x, that is greater than 1 by m, as n tends to infinity, is equal to 0. That is the conclusion we draw with the help of Borel-Cantelli lemma 1. Therefore, but this is by definition, this is the dm. Therefore, probability of dm is equal to 0. If probability of dm is equal to 0, then xn converges almost sure to x. So that way we can apply the Borel-Cantelli lemma 1, that is first part of Borel-Cantelli lemma, to prove the convergence of a sequence. Thus we can apply this condition, that is probability that mod of xn minus x greater than equal to 1 by m, that is the sum from n going from infinity. If that sum is convergent, then xn converges to x almost sure. But this is a sufficient condition. Unlike probability of dm is equal to 0, that is a necessary and sufficient condition, but this is a sufficient condition only. We shall consider one example. Suppose the random sequence xn is given by xn is equal to 0 with probability 1 minus 2 to the power n, and equal to n with probability 1 by 2 to the power n. So we see that this probability will become 1 as n tends to infinity, and correspondingly this probability will become 0. So therefore xn approaches 0. Now whether this is the limit we get in the almost sure sense, let us see. So we see that probability of xn mod of xn minus 0 greater than equal to 1 by m, that is equal to probability of xn is equal to n, because for n only it is this quantity is becoming different from 0. Here it is exactly 0, therefore only n we have to consider. Probability of xn is equal to n, that is equal to 1 by 2 to the power n. So we have to consider this sum now, sum of these probabilities. So if we consider sum up from n is equal to 1 to infinity, that is equal to sum of 1 by 2 to the power n as n going from 1 to infinity, and we know that this sum is less than infinity. This is a geometric series, we can find out the sum. So this sum is less than infinity, therefore this sequence xn converges almost 0 to x. So that way we can prove whether a sequence convergence to a random variable x in the almost sure sense. Let us summarize the lecture. Recall that this xn, this sequence of random variable, it represents a family of sequence. So unlike in the case of sequence of real numbers, the sequence of real random variables represents a family of sequence. Convergence of a random sequence is to be defined using different criteria. The sequence is said to converge everywhere to x, or pointwise converge to x if limit of x and s is equal to xs for all s belonging to s, that is the convergence everywhere. Now this sequence xn and going from 1 to infinity is said to converge to x almost sure, or with probability 1 if probability of this event, that is s such that limit of x and s equal to xs, that is equal to 1. So this is the definition of almost sure convergence which we have introduced here, and this is a strong mode of convergence. And then for testing almost sure convergence, we consider this event dm. What is dm? Lim sup of the event s such that xjs minus s xs mod of that should be greater than equal to 1 by m. So lim sup of this event, and this is given by this definition of lim sup only we are considering here. And now we have a necessary and sufficient condition. xn converges almost sure to x if and only if probability of union of dm m going from 1 to infinity is equal to 0. The test is simplified, that is xn converges almost sure to x if and only if probability of dm is equal to 0 for each positive integer m. Now using the first Borel-Cantelli lemma, we got a sufficient test for almost sure convergence. If for each m greater than 1, this sum n is equal to 1 to infinity, probability of mod of xn minus x greater than 1 by m. So if this sum is less than infinity, then xn, sequence xn converges almost sure to x. Thank you.